Okay. No, that's not what I want. There. There's the control panel. I see we have a couple of people have joined us. Good morning. If anybody wants to unmute and say howdy, somebody let me know that you're here. Hello, everybody. Can somebody say howdy? Welcome, everybody. Good morning. Would somebody let me know that they can hear me? Can anyone hear me? I can't tell.
Good.
Can somebody say hello, please, so that I know that you're listening?
Hello.
Hold on, let me get my volume turned up. Let's try it again.
Hello.
Okay, now I can hear people. I assume you guys can hear me as well.
Yes, we can hear you.
Good. All right, well, we'll get started here in about 3 or 4 minutes. Looks like we've got 8 of you here so far. Appreciate y'all getting up early. Welcome. Huh, we had somebody left. I guess that wasn't all that interesting. All right, I believe everybody is here, so it's time to go ahead and get started. Um, if I'm trying to, if you have something to say, if you have a question to ask, feel free to unmute yourself and say howdy during the lecture. And we're going to start off taking a quick look at the homework assignment and just run through some of the tips that I gave you guys. We've got a couple of days before this is due, but that could mean somebody might be in a panic. Okay, so creating the project, that is takes a little bit of navigation through the Code Composer Studio Resource Explorer to get to where you're going. They don't believe in short names, short directory trees, but it is very important to hit the IDE button to load it into your IDE. And one of the things that's interesting about Resource Explorer is that the same button that you use to do an install on your local drive also is used to uninstall. So one of the mistakes that I've made in the past is that I've had a package that I installed using Resource Explorer and then accidentally uninstalled it because I thought I wasn't sure, and so I tried to kick it off again. So something to be aware of when you're looking at Resource Explorer. Configuration. So since we're not using RTOS, we are using the driver lib to pull all this stuff together. You may not need to configure both the low speed and the high speed clock. I think I've done it to as a matter of style, that I kind of like to have all my clocks running. You do want to make sure your watchdog timer is turned off. So that will be your first call in main to hold the watchdog timer. And to get the clocks running, you're going to have to reconfigure the I/O pins so that they are used for the external clock. You'll do that with this call, this GPIO. Here, let me outline it for you. That guy right there will set up the I/O pins, and then you want this call to set the frequency, and for the high speed and the low speed crystals. Okay, so let's go on to the next, and so that's what we've got on this. Anybody have any questions at all on, oh, no, not true. Okay. Starting the crystals. This is one that everybody needs to be aware of because it's a this core voltage setting stuff right here. Set core voltage and setting the flash wait states. I'm recommending that you set this up for high-speed operation. This processor can run at multiple speeds and multiple voltages. If you do not set this up properly, the core voltage and the flash wait states, when you set this crystal running full speed ahead, the processor may work, it may not. It's going to do weird and wonderful things. Well, weird things. What else? Okay, so you've got the various clocks that you want to set to 48 megahertz, various clocks you want to set to 32 kilohertz. Again, you probably don't need to set all of these. I like to just to be thorough. And then, of course, you're going to need to configure your output pins. And then you can use this GPIO toggle output on pin to blink things on and off. Now, SysTick, I don't know how many of you have used the MSP432 before, but SysTick is a timer that is not available in straight MSP430s. It's only available in the MSP432. And its purpose in life is to be a periodic interrupt timer. It's not good for anything else. And it is part of the basic ARM architecture. So anytime you've got an ARM processor, there's going to be this concept of a SysTick. So to set it up, you basically turn off the interrupts. While you're configuring it, you're going to want to return it on. You have to set up a callback function for it, so that using this call, you can specify the function that gets called every time the SysTick timer expires. You have to enable the module. So this is another concept in ARM, and it has to do with the fact that ARM processors all have the ability to turn off various I/O modules. Sometimes they come up by default, but for the most part they do not, which means anytime you get ready to use an ARM peripheral, you need to be aware of the fact that it must be turned on. So the good news is that we're not doing a lot of we're not going to be doing a lot of stuff at the low level on this ARM processor, and so the RTOS library takes care of most of this concept for you, but it's something to be aware of on any kind of an ARM processor, that you actually have to enable it, because you can go off and set up all the registers and do everything that you're supposed to do, but if it's not enabled, then there is no power provided to that block. And lastly, of course, you want to set the clock period and set the SysTick interrupts. So does anybody have any questions about the homework before we go on to today's lecture? Cool. By the way, that's the story of my life. I've made lots of mistakes. All righty then. So today we're going to talk about task operation. Again, I encourage you, if I'm moving too fast, if you don't understand something, please speak up. So first of all, homework. There is a new Blinky assignment, and basically what we're going to be doing is we're going to be doing the same thing that you're finishing here for this coming Wednesday, except we're going to be doing it using the RTOS. So I want you, this first task is to get it done any way that you know how, basically. And the second task is to do it with the RTOS. In the meantime, I also want you to do some reading. Here, the few more sections in the user's guide for the kernel. I know last week's reading assignment was probably really entertaining. Y'all are looking to this one too, looking forward to this one too. So the question is, what is a task? A task, sometimes called a thread, really thinks that it has a CPU to itself and it never ends. So we talked about that a little bit last week. And what I'd like to show you guys is a little bit about how it is that tasks take up memory. This is a really important concept in terms of understanding how how an operating system works and how it can make a particular function think that it's all by itself. So let me first of all draw your attention over here to this code right here. So think of this code. It's over here to the right of the yellow line. Think of that code as something that you've written. This is a source file. It's got the main. It's got func A. It compiles and it runs. So let's talk about where in memory. So in any typical microcontroller, you're going to have both flash memory and you're going to have memory that is RAM. And in this representation, the only thing that I am assuming is going to be flash, non or semi non-volatile memory is the stuff that holds the program instructions. So when you think about what a compiler is doing, when a compiler goes off and it converts all of these statements to assembly language, it's going to end up with bytes of machine instructions associated, in this case, with main, with actually calling func A with parameter 3. And then it's going to have some assembly language instructions, some machine instructions that are associated with func A. Those actual instructions that the CPU is going to fetch and run through the core are stored down here in non-volatile memory, far away from the RAM. Now, if we think about this, let's go ahead and let's mark all of this. This is our RAM over here, okay? And the compiler is going to divide up all the things that take up memory into different locations. So the first thing that it's got to do, I've got these variables H and L, or no, that's H and I. H and I declared at a global level. So these are accessible in func A. They're also accessible in the main function. And so those are put in what's called a static area, and that's generally located somewhere down near, we'll call it the bottom memory. Most processors, you put this at low addresses. Some of that is because stacks tend to grow down, but you're going to put this down at low addresses down here. And so the storage for these two variables ends up being right in here, okay? Now, if you do mallocs and frees, there's got to be some sort of a heap where that memory gets borrowed out of. I don't have that as an example here because it's generally bad form in an embedded application to use dynamic memory. So I'm not going to reference it here. And in general, we won't be doing a lot of talking about dynamic memory during this class. So let's take a look at the rest of this stuff. So these variables C and D, this variable A, this variable B, in the C language, those are termed automatic variables. Now, an automatic variable is a variable that's declared within a function or within a subscope. So I don't know if you guys have used it. I generally don't encourage the use of it, but you could actually, within, say, a for loop, you could declare some variables that were local to that for loop. What makes automatic variables interesting is that they are always in C language, they're always put on the stack as opposed to some fixed location in memory. So what that means is that if this is our stack from here down to this area that we call unused stack, let me outline what that is. Okay, so stack extends from there to there, okay? When the startup code starts main, here's what happens. The first thing that it does is that it will, if these had to be initialized, it would actually push values. But otherwise, it's just going to move the stack pointer down far enough that there's room for these variables. The next thing that it's going to do is it's going to push these two arguments that we're passing to main. And we can talk at some other time about what this is. This is kind of a standard C thing for all mains. It's going to put argc and argv on the stack where main can get to them. And then, of course, it's going to call main, which puts this return address, the return address to the function that called main, onto the stack. So when main gets started, what is at the start of main, this stuff is all that's on the stack, okay? Now, when main wants to access C and D, it's going to access those relative to its stack pointer, which is pointing right here at return address. So it's going to add an appropriate amount of index to that to be able to access C and D when main accesses those variables. So main goes tootling along, and we're going to let's get that erased. So main goes tootling along, and main decides to call func A with his variable 3. So what's going to happen is that main, when main calls func3, it's going to push space onto the stack for these two parameters, A and B, right here. And then it's going to push the value 3 here, because that's being passed here to func A, onto the stack. It's going to call func A, and you're going to end up with a return address that's inside main on the stack. Okay? And all of this is under the control of the CPU and its registers over here. Okay? So the important registers that the CPU is thinking about, there's the flag register. It's probably called the status register, but it has flags. It has things like whether or not the last ALU operation had a carry bit set, whether the accumulator is 0, non-zero, those sorts of flags. There's going to be the stack pointer. The stack pointer is always pointing to wherever the current stack location is. Program counter, that's pointing to the particular machine instruction that's going on. Now, there are other registers in the CPU, and they're all going to be part of what's happening intermediately at that assembly language level in the code that you've written. And so there are some other registers that you might have to keep track of if you were, in fact, the CPU trying to do a unique program. So, by the way, this is being recorded and it'll get posted sometime this evening. Okay, so how does this task think that it's alone? So if I have 3 tasks that I have, they each have to have their very own stack that is independent. Okay, so the stack, as you recall, is right there. Okay, every function that's going to be a task has to have its own stack. Oops, wrong button. Okay, and when task 1 is running, it's keeping track. The CPU has its status, its stack pointer, its priority, its registers, all of that stuff, all running in the CPU. Now, the way this all works is that when task 1 is through running, before another task can run, all of the CPU registers that are being used, that's called a context. Important term here, guys. This will be on the test. The context for the task is all of these CPU registers that have the stack pointer, the status, it also has some stuff that's not CPU registers like the priority, what variables that the operating system is aware of, it may be waiting on changing, that sort of thing. And what it does is it copies this CPU information out of the CPU registers and into this task control block, so that all of this information is saved. And then, so let's say that task 1 is running, and task 1 says, you know what, I don't need the CPU anymore. Task 2 is the one that needs the CPU. Task 1 takes all the information from its context, puts it into this task control block, and task number 2 takes its task control block, shoves it into the CPU registers, does effectively a return, and starts executing as if it had never stopped. So in effect, what's happening is that every time we switch between tasks, the CPU stops everything that it's doing, makes a copy of it, and then returns a copy of the new task that gets started. So that when task 1 gets ready to restart, task 2 is going to take all of his information, put it in the task control block. Task 1 is going to put all of this information back into the context of the CPU registers, and all of a sudden the CPU now thinks that task 1 is really the only task that was available. Task 1 is running as if it had never stopped. So before I go on, let me pause for a second, see if there's anybody who has a question. Okay, I must be good. Task priorities. So the priority is what how you tell the kernel the relative importance of any task. This is not necessary. It's not a hard requirement, although it is a hard requirement with some operating systems. With the TI-RTOS, it is not a hard requirement that every task should have a unique priority. However, I will say that I recommend, in general, that you give every task a unique priority. The reason that you want to have a unique priority is very much the same reason that in life you want to have unique priorities. If everything that you do is the most important thing in the world, the fact is that you're going to be paralyzed, because you don't know whether you need to take out the garbage or cook dinner first. Now, priorities can change, right? So sometimes the garbage can is full. Maybe the garbage can goes up to a higher priority than dinner. On the other hand, if you haven't eaten all day and you're about to have a sugar meltdown, maybe fixing dinner is a higher priority. But the point is that in life, we all have to choose what a priority is. If you don't tell the CPU what priority a task is, the CPU is going to have some algorithm of which you have no control over that's going to pick. And when you have a computer picking things for you, Murphy's Law dictates that it will be picking the wrong thing no matter what. So for this particular kernel, the lowest priority task is 0, the highest is 15. Technically, the priorities are 0 through 15. 0 is reserved for the idle task. So the idle task is what the CPU is going to be executing when nothing else has a reason to be running. The idle task is really important in embedded applications, because the idle task is where you actually put the CPU to sleep to save power. In the case of the TI kernel, the idle task is always created automatically, and it is always a priority 0. So let's talk about how you're going to create a task with this kernel, with the TI kernel. So first of all, a particular task running with a context is called an instance of a task. Now, I'm going to go back a few slides here real quick. So, do you remember the context for a task is basically this set of registers pointing to a particular stack, okay? Task control block pointing to a particular stack. You'll note that those are not tied to the actual program instructions. So I can have a particular task that I have written, and I can actually set up separate tasks for two different instances of that task, okay? And so it would execute the same code generated by the compiler. So it only takes up this one chunk of ROM, but one version is going to be executing off of this stack, and one version is going to be executing off of this stack. So you can have a single task that maybe controls two different I/O pins, but in the same way, one set of code, one's running off of this stack, one's running off of that stack, and they're all happy campers. So that is an instance. So we can have multiple instances of a particular task, okay? Now, what it does have to have in the TI RTOS, this structure right here, task struct, is where the context is stored. That is the task control block for any given task. Now, each task must have its own, said this again, I'm going to say it more, must have its own structure and its own stack. Got to have both, okay? Task control block structure and stack, they must be unique for each instance of a task, okay? Now, generally, you're going to declare stacks to be arrays of character. Keep in mind that since things get shoved on the stack in pairs of bytes, a word at a time, that the size of your stack is only really useful if it is an even number. So you need to pick whatever the size of your stack is, that array, you need it to be an even number. And I will tell you that although we will find at least one exception to this, as a general rule, 512 bytes is a really good starting point for a task, and it will absolutely do for the first homework assignment. Now there is another structure called task params, and this has parameters that you're going to be using to fill in the task structure. Now, it turns out that there's a lot of information that you can pass to a task within the TI kernel. And all of it is going to be putting information in this task structure. But if in the calling parameters for this task structure, you were going for initializing this task structure, if you're going to put those all as calling parameters, there are probably 7 or 8 different parameters, maybe more, that can potentially get set in this task structure. So rather than having a very complex call, what the kernel designers for Texas Instruments decided to do was to have this other structure called task params that gets initialized to some good enough defaults for most tasks, and then you actually assign the things that defaults don't cut it for. Here we go. All right. So let's talk about this task param structure that I just told you about. Here are some things that you're going to be really want to be aware of that are in there that you're going to have to at least consider initializing every time you call this function. So the first one that we're going to talk about is stack. You have to put in here the pointer to the low address of your stack. Okay. Even though stacks grow from top to bottom, the calling parameter is actually set it up to point to effectively the bottom of the stack. And you have to put in the number of bytes that are in your stack. Okay. Priority. I believe the default priority is somewhere in the middle on the kernel. It's like 5 or 6 or 7. But again, if you don't set that, then everything is the same priority. So I suggest strongly that you pick a priority and assign that. These arguments here, these are values that get passed to the stack that are to your task that it can use at startup to change its behavior based on a particular context. And we'll talk about that here in just a minute. Oops. Okay. All right. So we talked about priorities, but we haven't really talked about yet how to figure out what priority you should assign. So first of all, priority assignment tends to be heuristic rather than analytic. And by that, what I mean is that going out and solving the math to figure out what priority number and relative to all the other tasks you should be assigning on any particular task would be a almost impossibly complex task. And so what we do is we use heuristics, rules of thumb. And some of those things that we ought to be thinking about are, number one, hard real-time tasks. Those should obviously have a pretty high priority, because if something goes wrong, as we talked about last week on a hard real-time task, bad things happen. Any task that requires low latency, okay, so any task that when something happens that restarts the task, it needs to happen very quickly, that should have a high priority task. And well, one of the other things that would be an indication of assigning a higher priority to a task is that if it requires low jitter. And by jitter, what I mean is that let's say that I have a task that is timer based, and so it's going to start every 100 milliseconds. If it starts at 100 or 101, everything is okay. If it starts one time at 102 milliseconds, and the next time at 99 milliseconds, and the next time at 103 milliseconds, and that causes a problem, that difference in timing of when it starts up relative to the last time that it was running is called jitter. And so an example of a task that requires low jitter might be a fast Fourier transform. So if you're implementing a digital filter in a control system, you absolutely need to make sure that you have as low a jitter as possible, otherwise the math stops working. So for other things though, how do we figure out what it is that we're going to be doing for deciding what's a high priority task, what's a low priority task? So there is a particular model that we're going to use to see about that, and this is called rate monotonic scheduling. Now, this is based on some math that people figured out that they could do. It is not necessarily based entirely on reality. The math here assumes that every task that you have is periodic. So, exceptions in real life Might be stuff coming off of a, I've got a serial port that's reading data that somebody types in. Well, that's clearly not periodic. But many things in the embedded environment are going to be periodic because it's going to be about control loops and that sort of thing. So the other thing that rate monotonic scheduling assumes is that the tasks don't synchronize, they don't share resources or data. So these are fully independent tasks. I don't have to complete task A before I start task B, etc. Or task A and task B, whoops, y'all didn't need to see that. Task A or task B don't have the, don't share data because you might have to stop task A while task B is doing its thing. Now, when you do all the math in rate monotonic scheduling, which is kind of the ideal best case for CPU usage in a real-time kernel, for everything to work properly, for every task to be able to operate with low jitter, low latency, and hard real-time tasks to all happen when they're supposed to happen, the total of all of the instructions used by these tasks has to use less than 69% of the CPU time. Now, what that means, let me put that in another way. For an RTOS to work properly and satisfy timing requirements, it is absolutely required that it spend at least 31% of its time twiddling its thumbs and doing nothing. If you're not doing that, then there will be times when you will not meet all your timing criteria. And it turns out that 69% is somewhat optimistic because not all tasks are periodic, and the tasks do, in fact, synchronize often when we design these architectures. But this is a good start. Now, why do you want to know that? Is this really about priorities? Well, some of it's about priorities, but the other piece is whether or not you have enough CPU to get the job done. The fact is that to make an embedded system work, you have to have a fast enough CPU that we're going to satisfy this. Okay. If you don't have a fast enough CPU to do this, then you have to either go with a faster CPU or divide it into multiple CPUs. So with rate monotonic scheduling, one of the things that you have to do is you have to figure out how it is are we going to assign priorities. And what you do is that if you take a look at how often a task needs to get executed, okay? So this is, let's say that's 10 hertz, that's 100 hertz, or excuse me, that's 10 hertz, 100 hertz, a kilohertz, how often things get executed. The stuff that doesn't happen very often, you give a low priority. The stuff that happens a lot, you give a high priority. So that's another rule of thumb that we can use along with, along with these heuristics. Another rule of thumb that we can use is that the more often a task is going to execute, the higher priority it should have. Are there any questions yet? Okay, so how do we start a task? With the TI kernel, here's basically what we're going to do. So first of all, you will note in our coding standards that I have this thing about magic numbers. You'll find that I try to define, although I missed one down here, see that argument? But I try to define almost everything as a pound define or an enum to put in numeric values. That's a good programming practice that we all should be in. Sometimes we get in a hurry and we just type in a number. The problem is that when something causes that number to change, then we got to go find it everywhere. So pound defined stack size. So we're using a 512 byte stack. This is my task control block task struct for task 0. And that right there, task 0 stack, spelling error, that is, oops, that should be, no, that's not a spelling error, that's correct. Task stack size. All right, tongue twister though. And then down in the body, when we get ready to start up this task, what we do is this task params inet. This initializes this task param structure that we're going to be using. I don't show the declaration for it. It's a local variable, not a global. And then I'm going to set this arg0 to 500. Not sure what that means in this case, but we're doing that. Set the stack size, and then you point the stack to the actual stack array that you've declared. And then you call this function called task construct. You pass it the task, your actual task control block here. You pass it a function. Okay, so heartbeat function is a function that I've declared that is my task. You pass it these parameters, and this is for an error return value if you choose to monitor that. And this is what my task looks like. So in this case, this is going to be toggling the board, one of the board LEDs when I start this task. And that argument that we pass down here, it turns out, is going to be passed to this function, task sleep. And task sleep, as you're going to learn here shortly, tells the task to stop executing, let other people have the operating system and the CPU for a certain number of timer ticks. Timer tick being defined in this case as how often sys tick kicks off. So what this does is that when we call this function, it goes in here and it tells the operating system, hey, you know what, I don't need the CPU for 500 ticks. And then after 500 ticks, the CPU turns this task back on and it executes this GPIO toggle. So it turns the LED on or off. And then it comes back here and it tells the CPU, you know what, wake me again here in 500 ticks. And so this task thinks that all it's doing is sleeping and blinking. But in fact, what it's doing is that while it's sleeping, somebody else is working. So this is a basic task skeleton. So the next thing that I want to talk about, oh, before I go on, are there any other questions about what we've just talked about? Cool. All right, reentrancy. So one of the things that has to happen, if I've got a function that's going to be called by more than one task, it needs to be designed in such a way that if I'm in the middle of that function and another task, and the task pauses, and another task takes over, that other task can't possibly cause something to go wrong with the task that's currently using the function. The ability to do that is termed reentrancy. So you want to aim for, as you design your software, making all tasks reentrant. Tasks that aren't reentrant must never be invoked twice, at least simultaneously. If you're going to use a non-reentrant function, you have to somehow protect access to it. We'll talk later on about how we might protect access to it, but for now, just know that you have to have some way to prevent that from happening. So let me show you a quick example of a task that is reentrant and a task that's non-reentrant. So a reentrant task all the variables that are used by this task are local variables, automatic variables in C. So these are a couple of examples of non-reentrant functions. So in this particular case, this variable barf, you will find as you take classes from me that that's one of my favorite, I don't have a good name for it, variables. So barf is a global variable in this case. And so this ls digit function that uses barf is not reentrant, because if I were to stop this particular function mid-execution, a different function could alter barf. So showing you how that might work, let's say that we're in this function, task 1 is calling ls digit, and it has just computed and assigned to barf this particular number, okay? And now another function calls barf, or calls ls digit. The barf, the value of barf, which somebody outside this function is going to depend on, will get changed by the other function that's the higher priority, and then when we return, barf is going to, this ls digit is going to return, but barf is not going to be the barf computed here, it's going to be the barf that was computed when the other function got called. So another example is this thing called print fifth. And you'll see how it has this static variable called count. And because it has a static variable called count, there's a problem, because what we're going to do is we're going to print, okay? We're going to call print fifth. You're going to send it a string. If this variable count is greater than 5, then we're going to print out that string. Otherwise, we're not. So it's not going to print until the 5th time around. Well, the problem is that if I call this in 2 different functions, then it's actually going to be counting every time from every task that called and incrementing that count. And so that's also going to give you an unexpected result. So that's non-reentrant. And we can look at the way that stuff gets stored in memory to talk about stuff that's reentrant. So anything that stores in this global area, so that is, you know, a global stores information up here, global stores information up here, statics stores information in this area as well. All of those tend to be, all of those are anything that references a variable in a global area is non-reentrant. So what I want to do, one way that we can protect global variables is that we can stop interrupts while we're messing with them. So if you stop an interrupt, if you stop a global variable during an interrupt, if you stop interrupts, then there will be no context switches if we disable the hardware interrupts, which means no other task can run while these interrupts are disabled. So now you can mess with that particular global variable and be safe. So within the TI-RTOS, this is a call that you want to be very familiar with. The interrupt disable, interrupt enable. In effect, this turns the kernel off. So you want to use it sparingly, okay? And if you have an interrupt function that disables interrupts, that can also cause you problems. So you want to do this typically in mainline code, but this can protect from potentially altering a global variable by another process taking over. So let's talk about, that's interesting. Why have I got, this is not, posted another copy of this. Let me, looks like my Google Drive didn't update. Hold on just one second. I'm going to stop this. Let's close that down. Let's see if this is, this got Rev 2 here. No. Okay. Let's see here. Ah. Let's do a quick retry on these. See if that's not going to work. So, come on, baby. By the way, this picture was taken a long time ago. He is 20 years old now, so he's not 20 in that picture. I apologize for the delay. I should have checked the version number on my slides. Made a change last night. Okay, that's taking longer than I wanted. So, over here. There we go. All right, so let's. Okay, there we go. All righty. That's too much. Okay, I wanted to go through a classic non-reentrant function and show you guys how to do it. But it's taken me long enough to get here that I think we're going to skip going through this in detail. This is in your slide deck that has been, I've re-uploaded the slide deck to eCampus, so Rev 2 is up there. Just real briefly, what's in here that I'd like you guys to take a look at so that you kind of understand what's going on. STR to toke, actually called STR toke, which goes off and it finds tokens in a string. So this particular function, you can see what this is. This is taking the string dash space, this comma space, where it says that a space, a comma, a dot, or a dash are, we're going to call delimiters. And it takes this string and breaks it up, and then it will actually print out each individual word in the string with the punctuation taken out. This is really handy if you're trying to parse up, you know, like a CSV file. It is a function that has been in the standard C library since the 70s. And the way this function works, this is the actual function, how it works. I've added comments. All the stuff that's online is without comments because they assumed that it was all self-explanatory code. What I want you guys to look at when you look at this code is that the fact that last S is a static and we have this operation in here makes str to k, str toke non-reentrant. If two functions are parsing two different strings in different tasks, this will blow up. And what I wanted to do was I wanted to show you down here, and then you can take a look at my code and see how it works. This is a better version of str toke. And what it does is by passing this variable out here that we can keep in the particular task that's calling, we can make this function that was non-reentrant into something that is in fact reentrant. So that's what I wanted to go over with you. And let's see if that is up yet. No, it's not. Okay. So now let's talk about our first pin. So homework assignment number 2, you're going to have to put the task to sleep. And so you need to be familiar with the operating system called task sleep. And basically what it does is it returns the control to the operating system for a certain number of ticks of systicks. So if you do what I tell you to, which is in fact you're going to set the systick to interrupt at every 500 milliseconds, then doing a task sleep 1 would sleep for 500 milliseconds. 2 will sleep for, or excuse me, 5 milliseconds. Is what we're telling you to do. So 1 tick sleeps for 5 milliseconds, 2 ticks sleeps for 10, 3 for 15, etc. Okay. So basically what happens is when you call this, it's going to change the mode from running to blocked, and it's going to wait for n ticks before it puts it back to a ready state. And we're going to do this on Wednesday, but what I want to do now is I want to bring this up. I want to talk about homework tips for doing the Blinky kernel. So when you get ready to redo Blinky, this is what you do to get it started. You're going to have to set up the GPIO. So the GPIO functions that you use with the kernel do not naturally know about the LED that is on the EDU board. That is what we're going to be blinking. So when you do this and it creates a project, one of the files that it creates in this project is MSP432P401R.C, which is the configuration code, effectively the board support package, for those of you who know what a board support package is, for that particular board. By default, it doesn't know about a lot of the stuff that you're going to potentially be talking to, so you have to go in and make an alteration to this code. So in this source file, what you're going to look for is this declaration for the pin configuration. You can see that by default, they have put in here the input pins that they're declaring, and this is declaring it port 1, pin 1, telling it that it's a GPIO configured with a pull-up, with using the internal pull-up. and it's going to give an interrupt on the rising edge. So that's switch 1. Switch 2, similar thing. He's on port 1, pin 4. And then you can look at the 2 output pins that they have declared. And so they've declared this LED 1, which is on port 1, pin 0. They've declared it as an output with a high high pull-up strength, and they have declared it to be by default configured with low. So when they initialize this, that pin will initially start off set to 0, and they've done basically the same thing with this red LED that is on that board. What we need to do is we need to tell it about the red, green, and blue LEDs that are on that are all in that single LED package on the EDU board. And so that's going to be port 2 pin 6, port 2 pin 4, and port 5 pin 6. We're declaring them as outputs. I see a few of you are bailing out. And we're going to start those off at low. And then you also have to go in and make corresponding entries in this header file so that you have so that you can appropriately index them. Okay. It's really important. There's another variable after this called GPIO count. You'll want to definitely make sure that these go in before that variable. And this is how you change the tick time. You can either open up the empty.cfg that gets created as a part of the system, or you can use xgconfig, whichever you prefer. So that concludes today's lecture. Yeah, are there any questions before we button up? All right then. Well, I will see you all bright and early on Wednesday morning. Looking forward to it.
Professor Willett?
Oh, yes. Yeah.
About 5 of us just dropped out. The Wi-Fi cut out on campus, so we missed the last 3 or 4 minutes.
Ah, so that explains why the folks dropped out. So we do have, I will post as soon as possible the recording so that you guys can get that information. You can just watch the last part of it. I certainly enjoyed it.
Okay, thank you.
Okay, thank you for letting me know. And we'll see you guys next week.